Thank you for the opportunity to speak here today. I want to divide this talk into two parts, and I want the second part to be less technical than the first one, and the first one to be really non-technical. So I hope to achieve this. So the starting point is what in algebraic geometry we call a curve. So it's going to be a compact Riemann surface. A compact Riemann surface has a natural invariant, which is G, which has many interpretations. For example, as a compact oriented surface is the number of holes. And I want to talk about vector bundles, complex vector bundles on it. The object in the talk essentially is the parameter space of these vector bundles with additional structure, moduli isomorphism. So these are called moduli spaces of vector bundles. So there are three flavors, and they correspond to the three different aspects that this object has. It has a topological aspect. It has a C-infinity aspect. And it has its complex structure, so a holomorphic aspect. And each of these aspects going to endow this numerator with the structure, with the appropriate structure. And then I will have three different flavors of these parameter spaces. So there's going to be a topological flavor, a C-infinity flavor, a holomorphic flavor. But then I want to talk about two reductive groups, the unitary group and GLN. So according to these two groups, I will have two pictures. This is GLNC. I will have these three moduli spaces that I will denote with the letter N and with the letter M. Now, depending on the flavor, you have three cohomologies that are natural. One is the singular cohomology. Some people call singular cohomology Betti cohomology. So this moduli space will correspond to this interpretation. On a C-infinity manifold, you have differential forms. So here there will be the de Rham interpretation. And on this holomorphic compact manifold, you have the splitting of the holomorphic forms in their DolbeaultMDolbeault pieces, the holomorphic and anti-holomorphic part. So here there will be a DolbeaultMDolbeault moduli space. And the same here, B, DR, and DO. Now, the first part of the talk is a discussion of these objects, culminating in the non-abelian Hodge theorem, which is stating that there is a natural diffeomorphism between the first and third. It's true, there's a natural diffeomorphism between all three of them, but I will focus on this in this talk. So there's a natural diffeomorphism. I put R just to remind myself that these are complex manifolds, but this is a diffeomorphism that is neither holomorphic nor anti-holomorphic, so it's truly mixed in this sense. Now, given this is the statement of the non-abelian Hodge theorem, and given this isomorphism in cohomology, there is an isomorphism in cohomology. And the second part of the talk introduces further structure on these cohomology groups in the form of some subspaces, some filtration into subspaces, which on this side I will denote by WB. W stands for weight, and in this side we will have a different filtration that I call P-Dol, which stands for perverse Leray. I will try to explain both of them. Now they're defined and depend on the complex structures here, which are different. So the statement of the second part of the talk is that under this isomorphism, they correspond to each other, at least for GL2. That's my talk. So now I want to focus on this part, so I want to explain what's going on here. So maybe the best way to start is to take the case of rank 1. So let me start with U1. So there are the three flavors. Let me start at the left-hand side, and let me take, in topology, the most natural vector bundle you can start with on a space is a locally constant vector bundle with transition functions given by constant matrices. So they are the same thing as representations of the fundamental group. So this is the fundamental group of the surface X. Now you want to identify these representations according to a natural isomorphism relation, which is conjugation on the target. But this is abelian, so I say this because later UN is not abelian, so we have to do that. So here you don't do anything, but I write it anyway. Now here, it turns out the right object to consider is a flat unitary bundle. Connection. Now, in the background, I should say that I fixed this complex line bundle, the trivial complex line bundle, with a trivial metric on it, with the natural Euclidean metric on every fiber. So it makes sense to talk about the U1 structure, because I'm going to respect this metric. And then I take the U1 structures which are flat, and I mod out by gauge equivalence. And on the third side, I take holomorphic structures on the C infinity bundle L. I denote it by a script to remind myself these are holomorphic. So holomorphic structure. And then I mod out by isomorphisms among these holomorphic structures. So now, what is the connection with the words Betti, de Rham, and Dolbeault? Well, here, this is nothing else but the first cohomology group, singular cohomology group of the surface with coefficients in the circle. Now here you have to think a little bit. So first of all, you fix the obvious connection. And every other connection is obtained by taking this one and adding a differential form. So I can express the numerator as D plus a differential form. But then I want it to be flat. That means the form is closed. And then I want it to be unitary. That means the form is imaginary. So I have imaginary closed form modulo the gauge action. The gauge action, what is the gauge group? So the gauge group is just isomorphisms of the line bundle, but because it's rank 1, these are the same thing as infinity functions. To C star, but because of the Hermitian, the unitary constraint, they land in here. So these are functions like this, and the action is addition by d log of the connection, d log of the gauge. So now I have to take closed imaginary forms modulo this. Flat is closed, so first I get the de Rham group, and then I have to divide also by the fact that these functions have an argument. So at the end, I get I times the first de Rham group with coefficients in R divided by 2 pi I, the first cohomology group with integer coefficients. Now here, I start in the same way. I have this nice description of the complex structure on a line bundle, which is given by operators of type 0, 1. This is a theorem by Kouzul-Malgrange. So instead of D, I take D bar. And then I have to take D bar plus a 0, 1 form, and then mod out by the gauge. But that boils down to taking just the anti-holomorphic forms. Modulo gauge means that, as here, I divide by the image of the integral cohomology. So now the nice thing is that here, these three things are connected, because I can start with my form and take the exponential of the integral over a homology cycle. And this gives me a representation. Or I can take the anti-holomorphic part of this closed form. And then the nice thing is that these are isomorphisms. In fact, you can view this as a de Rham theorem with denominators. And you can view this as the Hodge theorem with denominators, the denominator being the lattice. Now, this is an isomorphism of real Lie groups. But there's a new feature here with respect to the first two. The third one is also a complex manifold. By Hodge theory, this is a full lattice, and this is a complex torus. However, this is a complex manifold in a natural way, but these are not complex manifolds in a natural way. So it doesn't make sense to ask whether the maps are holomorphic. Now, in fact, this is a famous object. It's called the Picard torus. But because even if this has no bearing on the rest of the talk, I'm an algebraic geometry. At this point, it's irresistible to say that this torus, which is called Picard, is also naturally isomorphic to a torus, which is called the Jacobian torus. And this is part of a beautiful story, because if you take integration on the Riemann surface, you can set up an isomorphism between the anti-holomorphic forms and the dual of the holomorphic forms. And then you divide by the lattice given by integrating along homology cycles. Then these two are the same. Naturally. Not the same, but naturally the same. And this is the Jacobian torus. And this is the modern geometric object that underlines the Abel and Jacobi theorems. So even if this has no bearing, obviously an algebraic geometry can always saying this. Okay, so this is the story for U1. So now what is the story for GL1? Well, you just take P into GL1. Again, you divide by GL1, which is abelian. Here you take unconstrained flat connections, modulo gauge. And then here you take, and this is a bit tricky, but anyway, let me say it. You take the holomorphic structures, take pairs, holomorphic structure and differential holomorphic form. I'm not going to try to explain why this is natural, but I'll give you an explicit map between the three spaces. And I'll try to say the keyword that allows you to define a map from here to here. Now, the map from here to here is the obvious map. You take the form and you integrate, so that's the holonomy of the connection. So this is the holonomy. And here is the existence and essential uniqueness of the so-called harmonic metric for a connection. Let me just say this. before we took our imaginary form and we took its anti-holomorphic part. Here you take a form and you would say, okay, let me take this, but that doesn't work. I cannot take the anti-holomorphic part and expect to have a natural construction. You have to use this guy to produce a harmonic representative of something associated with this. So that's a subtle point, and I don't say anything more about this. But then when you do all your calculations as above, here you get H1 deRam with coefficients in C, model the integral lattice. Here you get H1b of X with coefficients in C star. And here you get the Dolbeault space of anti-holomorphic forms divided by the integral lattice times the holomorphic forms. There's a natural way to see this. I mean, no. Once you do this and you do the calculation, you can see that it works like this. You take a anti-holomorphic form, take a holomorphic form, and then the map in this direction, I write it because I want to comment upon it. It's this. Maybe the plus and minuses are mixed up, but it doesn't matter. The point is that this is clearly not holomorphic, and it's clearly not anti-holomorphic, so it's clearly mixed. There's no hope. So what you have here is three complex Lie groups with a biholomorphism between the first two and an R isomorphism between the second and third. Okay, so these are the spaces that in rank 1 I denoted by n. And these are the spaces that in rank 1 but unconstrained by just the GL1 I call MB, M deRam, and M Dolbeault. Okay, so what's the story in bigger rank? So the story in rank 2 or in rank 1, no, sorry, in rank 2 or higher. Now this is where the story actually becomes very interesting, because this picture is completely generalized, but in a highly non-trivial way. So the first object was defined by Mumford, and it's the moduli space, the parameter space of vector bundles modulo holomorphic vector bundles, modulo isomorphisms. Now, there's a key thing that one has to mention. One has to take stable holomorphic vector bundles. So I'm not going to define what stable means, but I actually can use the word of the person who invented them when he actually introduced them to the world in his ICM talk. Mumford said, well, let's think about this as follows. Introduce a certain notion of positivity on the vector bundle, which he calls stability. He calls slope. And then you call the vector bundle stable if every subbundle is more negative. So by saying this, I didn't say anything, but at least at least I don't have to explain what this is. Okay. Anyway, Mumford constructed this in 1962, and this is a complex projective manifold. Of course, here I'm cheating a little bit. I would have to talk about degrees of vector bundles. I don't want to do that, because if the degree is 0, for example, this is a singular space. Actually, no, it's non-compact. But then you can add something, you make it compact. So I don't want to get into that. So let me just say that let's pretend it's okay. If the degree of the vector bundle is 1, it's okay. If it's 0, you just have to tweak things, but then you get a singular projective manifold. Now on this side, it's natural to take the representations into UN, but now you have to divide by conjugation. Now there, before I mentioned stable, I took everything, and that somehow turns out to be bad by the work of Mumford, so you got to do this. Now, if you take this, this is also bad, and you don't need the notion of stability to understand this. You just need to take this matrix and conjugate it. And then it is conjugate to this, and as epsilon goes to 0, you go towards the identity. So you have different Jordan canonical forms being having orbits that actually collide. Yeah, but let me, okay. You're right, yes, but of course, this is a general problem. Yeah. Of course, I understand, yes. But then you would have complained about everything else I said so far. Okay, so this hits the identity in the limit, and so the orbits are not closed, and so if you want to divide, you don't get a space which is good. So you got to throw away, for example, the ones that are not irreducible. So you take the reducible representations. Now this is the Betty side. This is the holomorphic DolbeaultMDolbeault side. What to put here? Well, this is subtle. Let me get to it later. First of all, there is a beautiful theorem by Narasimhan-Seshadri that says that these two objects are the same up to diffeomorphism. So this carries no natural complex structure, but it's naturally diffeomorphic to this projective manifold. So this is a stunning statement. Also note that it puts close to each other two spaces where on one side you can use differential topology to study the geometry, and on the other side you can use algebra geometry. Now the third object, which is the de Rham object, is subtle. Well, first you start with the unitary flat connections, and then you divide by gauge. But this is enormous, so it cannot give you the right size moduli space, finite dimensional. This is going to be infinite dimensional. So the idea to actually make this into the right object was given by Atiyah and Bott. You need to cut down the space of connections by some equations so that you hope that the resulting space is finite dimensional. Of course, this is easier said than done. Which equations? So somehow they come up with this wonderful idea of considering the Young-Mills equations. So Young-Mills connections, modulo gauge is the right object. This is their theorem. And then they prove that these spaces are naturally diffeomorphic. However, these are no longer Lie groups. So we left that world. That's rank 1 world. Now the story for GLN is similar, but again, one needs two new ideas. Here you just replace UN with GLN. Well, what to put here, de Rham, and what to put here. So let's start with the de Rham side. This was the discovery of Hitchin. Instead of Young-Mills functional, it takes the self-dual equations on a Riemann surface. So it cuts down the space of connections to the right size, so that when you divide, you get a finite manifold. Then the holonomy gives the diffeomorphism. Now a second new idea is to understand what you have to put here. So I'm not going to explain too much. I will do it just by analogy. Now remember when I mentioned that you could go from here to here with your harmonic metric? Well, there's an analogous procedure. Before I say what's the end result, you need to reinterpret the form as a map. From the holomorphic line bundle to itself, twisted by the complex cotangent line bundle. So a form is the same thing as this. So it looks weird, But in higher rank, it turns out that it's the right object to consider. You want to take the pairs given by a holomorphic bundle and an endomorphism with twisted coefficients. You want to introduce the appropriate notion of stability. And if, sorry? Well, by this I mean the anti-holomorphic tangent bundle. Sorry, it's just a notation. Yes, you're right. Yes. Okay, then the great idea here is to first to find these equations as the right equations, and then to find this new notion of stability for pairs, and then. Okay, now the fact is that, in fact, sorry, this is a holonomy operator, so this is actually a biholomorphism. Instead, this is for the same reason that already occurred in the rank 1 case. This is just a diffeomorphism. All these are naturally complex algebraic manifolds. So now this is what we call MB, this is what we call MDRAM, and this is what we call MDolbeault. So now we have discussed the existence of natural diffeomorphism here and natural biholomorphism here. Now this takes the name of the non-abelian Hodge theorem, because in the rank 1 case, it was the usual Hodge theorem and the Ram theorem for the Riemann surface X. So by analogy here, you call it Hodge theorem because there's a better reason to say this, but just by analogy because of the rank 1 case. And it could also be called the non-abelian de Ram Hodge theorem, but anyway, that's the name. So non-abelian Hodge theorem. Okay. So I think this ends the first part of my talk. Maybe let me just say that maybe I should mention that in this case, this picture is interesting in the higher rank case, of course, because now you have these manifolds and they're diffeomorphic and you want to study them, and now you have at your disposal methods of differential topology, methods of gauge theory and Morse theory, and methods of algebraic geometry, both over the complex numbers and over the finite fields. And by work of many people, that it's too long to list, for example, the cohomology ring structure of this space was determined using all of these methods. Now, these are also diffeomorphic, so the cohomologies are isomorphic, but except for the case of GL2, the ring structure is not known. The Betti numbers are not known. So there are some subtle points here. However, in the case of GL2, one knows a lot. Okay, so now I can pass to the second part. Now I want to discuss the symmetry for GL2. In order to do that, I have two choices. Either I write down some formula or I take a simple case and I discuss it. So my choice, of course, is the latter. So I take the case of genus 2 because I can write out the cohomology without having my hand fall down. So because it's the cohomology gets bigger and bigger with the genus, but with genus 2 it's manageable, and I want to write it out so that I can discuss my goal. Okay, so first of all, remember there is this Riemann surface, and then I can take the product with the parameter space of vector bundles. Now, up to some contortion, there is a vector bundle on this product with the property that if you restrict it to x times m, where m is isomorphism class of the object, you get that object back. This actually is a subtle point, but there's no reason to discuss it now. So now you have the Q-net formula for the product, and you can look at the second Chern class. Now, according to the Q-net formula, it gets broken up into three pieces. Now I gotta write this. So first of all, it's in H4 of x times m. So I can write it like this: 1 tensor b plus point tensor A plus sum epsilon j tensor pj. So let me explain. This is the fundamental class of the curve, and this is the Q-net component of this object inside of here, call it B. So this is a class in the fourth cohomology of M. Now pick a symplectic basis for the homology of the curve, and then again you gotta find classes here in the Q-net decomposition. These are in H3, and similarly I take H0, I take H4 represented by a point, my curve, and here H2, and here I get my class in H2 of my M. So now I can write, it's a theorem, I can write the cohomology of M using these classes. So the result is, let me look in degree 0, and it goes all the way up to 6. I got the 1, A, P, A square, B, AP, A cubed, AB. I consider this as a graded vector space, but then there's one piece missing. The theorem says that you need to multiply by the cohomology of the Jacobian torus. Now this is a presentation for the cohomology of M. Now this is a distraction for what I want to say, so let me just erase it. It creates no problem erasing it. So now I have these classes. Now this is a presentation, this is the cohomology for M, whether it's betted or borderline. Now the point is that these are three different complex manifolds, and they're algebraic manifolds. So I want to claim that this picture is the flattening of something that I haven't discussed yet that we're still missing. So this picture is too flat, and it doesn't give us the whole perspective. So the point is that I need to consider the weight structure on the cohomology of these manifolds. So which is of course due to the linear. Now, what I need to say for today is the following, that the cohomology of every complex algebraic variety contains subspaces. Let me write them like this. Finitely many of them. I can consider their graded pieces. And these graded pieces break up naturally into PQ pieces, exactly in the case as the Hodge decomposition on a compact Kähler manifold. They're the usual symmetries by conjugation, etc. Now, naturally, a class which is non-zero lives in one of these, and there is an earlier moment, an earliest moment, k, where it lives in wk, but it doesn't live in the previous one. You call that the weight of the class. So if you have a class, you may live in here, but not in here. Then you say that this has weight k. Well, it's a theorem. Now I can add this extra dimension to the presentation of the cohomology. Instead of looking at it vertically, let me look at it as a matrix, where I also introduce the weights. They go from 0 to 12. This is a theorem in general by Hausel-Villegas. Sorry? Sorry, I didn't say the Betty one. So sorry, this is for the Betty one. This is the picture for the weight filtration on the Betty model. Okay, so now you see that you have more information here than you had before. Now this is on the Betty side. If you go to the Dolbeault side, I will not mention, yes?
So is there a relation like p squared, because p is going to be 3, right?
Yes.
Is it a multiple of AB?
Sorry?
I was just trying, I mean...
Yeah, no, the fact that there are some relations, yes. And this is the end result. The relations were discovered by Hausel and Taddeus, and they're a real pain in the neck. But in this case, they're kind of not so bad. Okay. So now we have more information. So the natural question is that, remember, we have the Dolbeault, the Betty space, and the Dolbeault space. Now this has its filtration, weight, but this is also a new algebraic variety, so it has its weight filtration. Now this is an isomorphism. Now because these are two different algebraic manifolds, even if they're differomorphic, there's no reason why these should correspond. And in fact, they don't. It's easy to compute the weight filtration here, and it's trivial in each degree. This means that A would live here, P would live here, B is in the right place, and so on. So it would be a completely different picture. So they don't correspond. So the issue, the question that I want to raise, because I already know the answer in GL2, is what, under this isomorphism, what filtration in here corresponds to this? That's the question. Okay. Now I need to discuss a property that Hausel-Villegas discovered in rank 2 and conjectured in higher rank. This property is called the curious Hardt-Lefschetz. Now this curious Hardt-Lefschetz, I want to explain what it is, but before I explain the curious Hardt-Lefschetz, let me remind you the classical Hardt-Lefschetz. Let me do it with a surface. It's true in general. You embed it in some projective space, a compact complex surface, projective. and then you take a hyperplane, and you take the Fubini's 2D metric here. It gives you a Kähler form. You restrict it to S, and you call that form H. So H is 1, 1. And it's a Kähler form. And with respect to cupping with this Kähler form, you get an isomorphism as follows. So if I cup with this form, I get this map, and this map is an isomorphism. How does it look like? Two for the dimension of S.
Oh, it's a surface.
Yeah, sorry, I said it by two-dimensional. This is, of course, true in any dimension. Just I want to write down now how it looks like. We have H0. Under the cup product, H0 goes to H times H0, and this lives in H2. But there's a complement, which is called the space of primitive classes, which I denote like this. And then I apply H again, and I get H squared H0 in H4. Then I go back, and I write down H1, and then here I write down H1. So when I write the theorem, it looks like this. I want to look at it like this, because here I have this string of operations, and I have this string here, and then I want to write it like this. So I represent the cohomology like this, and now I have a symmetry like this. Okay? But that's the same symmetry we have there. If I did this right, I would have to move this by one place and this by one place. And if I do that, it would look like this. Does that make sense? So cupping with A gives me this string, which I wrote here. Yes. Well, not a priori in this case. Certainly in that case of the projective manifold. Well, because I just want to point out that here I have a string with 3 terms, and here I have a string with 2, and a string with 2. To stress the symmetry, I move it, just for pictorial reasons. Yes, but how to say? But that property is not with respect to the weight filtration. It's with respect to the monodromy of the operator, which is completely different. So it's non-trivial statement here. The two are opposite, but that's a theorem. So the statement is that this is the presentation of this, where I stress the weights. And now I claim that under the cup product with the class AK, I take the graded part for this weight filtration in degree top minus 2k in an arbitrary cohomological degree. And then I go in GR WB top plus 2k in H plus 2k. Okay, and the statement is that this is an isomorphism. Now, the weight filtration is increasing. The monodromy weight filtration is increasing, but it's a different one a priori. It goes actually, well, I don't want to say it, but in this picture, it goes in this direction. And in this picture, the weight filtration goes in this direction. So at the end of the day, they will be opposite, but they're certainly not equal. So this is a non-trivial statement. Now, this is a symmetry that was pointed out by Hausel and Villegas. And in fact, it has its roots in another symmetry noted by Alvis and Curtis, which is the Alvis-Curtis duality for the representation, for the table of characters of GLN over a finite field. And then they looked at that and they guessed this. Then they proved it for GL2. So, okay, this is important, so let me write it better. This is the Curious-Ardlev. This is a theorem for n equal 2 and a conjecture for n greater than or equal to 3. Under the cup product operation, this is an isomorphism. ROP, sorry, where? Top, the top degree. So this ends, in this table we finish at 6. So top is 6. You always know what the top degree is. It's exactly the dimension because it's affine. Sorry? That's the top weight, not the top degree.
Oh, okay.
You see?
Oh, okay.
You see, you can have a class in degree 6 but weight 12.
Oh, the degrees are going down. The weights are going up.
No, they're both going up, but the weights are going up faster.
No, which table? The weights are up to 6.
Degree up to 6, weights up to 12.
Yeah, it's just the way it's. Oh, I see. You can tell it there, John.
Yes.
It's top weight or top degree? Top degree.
This is top weight.
Top weight.
Yes. And for every...
No, it can't be the top weight because you get to go to top.
No, not the top weight. Sorry. Okay, sorry. It's okay, sorry. It's the top weight in the cohomological degree I'm considering in that moment, which you can figure out from the table.
So it's the complexity depends?
Yes. So actually, the answer is yes, and the sentence I said before is not true. So yes, sorry, yes.
So is x here a curve or x just a smooth projected line?
No, x, it's, well, you could ask whether things like this happen in higher dimension, but I have no idea. So x is a curve. Yes.
And that moduli space that n varies over he's not projected.
Yeah, but let's not worry about that.
We're not worried about
No.
So am I right that this is trivial for Dolbeault?
What's true for Dolbeault?
If you make the same statement for Dolbeault,
No, it's truly false.
Okay.
because the weights are all the same as the degree, and then when you write it up, here you have one class and here you have two, so it cannot be true. You cannot have an isomorphism. So because it's non-projective, you don't have that symmetry. That's a point I want. Yes.
Dolbeault is pure, right?
Yeah, but
Everything is pure, so
yes.
you have some kind of Lefschetz.
No, not on a non-compact manifold.
Ah, yeah.
Yeah. That's important. Yes.
And so what happens for the RAM?
Well, for the RAM, the weights are the same as for Dolbeault. But so it's not interesting for this story. But that's because we weren't able to understand if it's important for us. So, but from this point of view, it doesn't say anything new. But that's clear because it goes to the. It goes. How does it work? Well, yeah. Well, I cannot explain some other time. Okay, so. So this is called curious because the underlying space is non-compact. And it's curious because the class A, as you can see there, it's of weight 4. So it's in its Hodge type, it's 2, 2. Instead, the Hodge-Lefschetz theorem is for classes of type 1, 1. So it's curious because of these two things which look wrong. Now, why did I mention this? Well, because now I want to, let's see, yeah, I hope we go to go. Yes. Well, that's what I said about the degree. If I fix d equals 1, then yes. If you take d equals 0, you can study the situation, but the space is singular, and honestly, I don't know what goes on there.
When you use back-to-back matrices, how do you prove it?
Sorry?
You say it's proof for GL2.
Yes.
Otherwise, the conjecture
That you know all the relations in cohomology. And they play things against each other. And
The proof is only adding or
well, yes and no. The proof is counting, and then there's an argument by Nick that allows you to go from the counting to the type, and then you go from there. Okay.
you count this over finite.
Yes, you count the representations. Yes.
So it's the cohomology state.
It's well, yes and no, in the sense that in every cohomological degree, you may have different Tate blocks, canonically split, but of different type KK. Type, for example, here. Here you have 2, 2 and 4, 4. In that sense, yes, it's Tate, but yeah, there are no extensions. Okay, so yes, because otherwise I have to write many more things and it doesn't illuminate.
So it means you work with SL.
PGL2. Yes. SL2 is more subtle. Yes. Yes. Okay. Oh, no, I need this. Yeah, SL2 needs a different kind of tweaking at the very end. Yes, so I need, on the DolbeaultMDolbeault side, I need a Lefschetz theorem that's supposed to be the counterpart of the Courier-Lefschetz theorem. Okay. So remember, I was looking for the filtration, but it turns out that looking for the filtration goes hand in hand with looking for a hard Lefschetz counterpart. So now I have to remind you the case of the curve, where our MDolbeault for the case of rank 1, where MDolbeault was just the cotangent bundle of the Jacobian. And now this is a space that, for obvious reasons, admits a natural map, because this is non-canonically isomorphic to the Jacobian times CG. So there's the projection. There's a way to write down this canonically. If you view this as pairs, holomorphic line bundle and endomorphism, and then instead of just taking the projection, you forget you have this and this, you look at this, and you just map from this space to an affine space by taking the characteristic polynomial of the endomorphism, which lands you in a space of tensors, which you can write down easily, and has this, this dimension, obviously because it's the space of holomorphic forms. So you do that in higher rank too. So this is Hitchin discovered the structure in higher rank. This is really remarkable. There's the characteristic map that lands you in some affine space of half the dimension. Now this is remarkable because there's more to it. This is an algebraically completely integrable system, but I'm not going to say what that is, because I just need to tell you right now that this is a proper map. And this is a second theorem that each improves, and it's quite hard. The general fibers are complex tori, which also have a beautiful geometric description, which I don't discuss. But other fibers are very singular. So in our search for this, let's focus on this. What about the hard Lefschetz on the fibers? Well, the hard Lefschetz on the fibers, first of all, with respect to what? So the important thing is that A was 2, 2 when you looked at it on the Betty side. The cohomology class in degree 2 was 2, 2. But on the DolbeaultMDolbeault side, it becomes 1, 1. So you can ask if you have the hard Lefschetz on the fibers. Well, on the fibers, it's positive. And on the fibers which are smooth, you get the hard Lefschetz. Do you have the hard Lefschetz on all the fibers? The answer is no, because you pick a particularly bad one, you inspect it, and you see it doesn't work. For example, the central fiber of the origin, you know everything about it, because it's a retraction of the whole space. So you have the Betti numbers, and you cannot have the Hard-Lefschetz theorem for the reason discussed before, because you have 1 there and dimension 2 there, so it cannot work. So now there is the final piece that puts the things together. There is a natural filtration on the cohomology of this space that gives you a Hard-Lefschetz theorem. Now, this is through the machinery of perverse sheaves. Now, of course, this originates in the work of Mark and McPherson, continuing with the Riemann-Hilbert theorem correspondence by Kashiwara and McBoot, and through the theory of perverse sheaves over finite fields by Berlinson, Bernstein, Delin, and Gabber. So this is a complicated machinery, but it gives you a filtration called a perverse filtration on the cohomology of the total space of any map.
Because the bow guy is smooth.
Yes, but it doesn't matter. It's in general, you get a filtration. And for any map. So using...
The concept should have to be reversed, right?
No. No. So take any complex, push it forward, and take the truncation downstairs. Gives you a filtration upstairs. So you get a perverse filtration here. Now I gotta finish on time, so I would have liked to say that using algebraic topology, we know what the Leray filtration is for fiber bundle, using cell complex structure on the base and pulling it back, and taking the restriction map from the total space to the pullback of the scalata. That's the way classically people think about the Leray filtration. You can do something similar here, but not with the scalata, which are objects that don't exist in algebraic geometry, but with some algebraic varieties inside of here. Let me skip that. The point is that you get this filtration, and then you have a Hard-Lefschetz theorem called the relative Hard-Lefschetz theorem, where Gr of this perverse filtration in degree, again, top, let me not say what top is, top minus b goes to Gr p top plus b, H star for Dolbeault. And this is a deep theorem, and this is an isomorphism. Well, I'm afraid where did I? Yeah, here it is. Well, now you have these two equations, and I think there's only one natural guess, that the weight should be, weight filtration on the Betti side should be exchanged into the perverse filtration on the other side. This is due to myself, Hausel, Migliorini. Note the halving of the indices here. So if I have top minus b, P Dolbeault will go to W, but in weight top minus 2b. So this is a theorem for GL2. Now let me finish by saying that we observe this for GL2, but we don't have an explanation. It would be nice to understand this a priori for some reason. Not the proof, but why this should be expected. Well, we prove it. Let me put it this way. Explanation, and then another explanation for why these things are doubled. That's really no conceptual explanation for that either. Now, you can ask the same question for any complex reductive group. So maybe I finish my talk by saying that we're working on GL3.
Thank you very much.
Yeah. No, the answer is no, it's a stack. But maybe in the cases that I shouldn't say it. I only been thinking about GLN and PGLN and SLN. Most of the words make sense for a complex reductive group, and on some big open sets you have a good moduli space. But yes. So the answer is I don't know and probably.
Well, I'd like to thank Mark again. Let's see the big picture here.
Well, obviously we are not seeing it. We're missing something, obviously, or maybe it's just a coincidence. But I don't believe it's so complicated coincidence. I don't believe. But also, I don't have good feeling about these moduli spaces personally. So. That's why I hope I kept it to elementary. I tried to fend off the technical questions.
What else can you do, right? No, you solved the whole I'm sure everybody got something out of it.
Okay, good. Hi. Yeah, sure.
Well, I have a question about this because it turns out when in higher rank, you always get a lot of singularities. Is that basically one of the things that's going on here?
So my understanding is that in higher rank it's still smooth. If you take
If
for
you
example,
take the right
coprime
situation.
degree, yes. So
Oh,
for
it is
example,
still high.
in degree 0 it's singular.
I know
If you
that,
take the
but
semi-stable,
Oh,
yes.
if you no, I'm assuming. Oh,
Yeah, yeah.
okay, so that isn't the problem. I see. So a lot of these questions, is that Housel that was it?
Yeah, Hausel, Tamás Hausel, yes.
He
Well,
was my colleague.
Yeah.
And I didn't, I mean, I think
Of
he's
course,
done this
yes.
work since, he hasn't been in Texas for quite a while.
Well, but he's looking at the same object since he was a grad student, but always
Yeah.
with a new perspective. So
Right.
it's a very complicated, it's expanding in many directions. I only see a very small corner.
So which, is that, the theorem of Hitchin about integral systems?
Yes.
Is that in the, that isn't in the original paper, that's in
It's in
it's somewhere in there, I mean?
I
I've been working on that.
I
paper
think
for
so.
many
I think he proves that. I think yes. I think
Right,
so. Yeah.
that's
For
actually-
GL2,
yeah, that's
SL2 actually. Yes. He works
Oh,
with
for
SL2.
SL2, but
He
not-
works for SL2.
That's right, but I mean,
But in
that's why I
general-
asked the question for higher rank, because somehow, I mean, for GL2, I mean, from some point of view, it's just that you're just putting several complex structures on